Alright class, welcome. Sorry I can't be with you guys today, so I went ahead and decided to record a little video for you guys to help you make sure you understand exponential growth and decay. So we're just going to continue on from our lesson yesterday. Hey, make sure you're paying attention there. William, talking to you. Okay. Alright, so exponential growth and decay. We talked yesterday about y equals ab to the x being our format for exponential growth and decay. All right, what we're going to be talking about today is applying it in some real life situations with what's called our exponential growth model and our exponential decay model. All right, so write this down. We talked about in order for this to be growth, b had to be a number greater than 1. So we're going to have another formula that's just very similar to it. All right, the formula is going to be something like this. All right, so A in this case is our initial amount. So whatever I'm putting in, so whether that be money or whether it be trees or bacteria, whatever it is that's growing exponentially. All right, R is our growth rate. So usually they'll give it to you in like some sort of percentage, 8% growth, 9%, 22%. Notice how, because I'm adding it to 1, that's why it will be growth. So if it's 22%, that'd be 0.22. So 1 plus 0.22 is 1.22, therefore greater than 1, hence growth. All right, and lastly, those of you who are pretty smart could probably guess, T stands for what? Time, yes. All right, therefore, Y would represent our new amount. Okay, now time is usually in years, but sometimes they'll say, all right, this is our growth model, and it's being applied for every 3 months. And so if they said, after 12 months, how much was there? You say, all right, well, how many 3-month chunks are there in 12? Therefore, 4, so T would be 4. But usually it's yearly. You'll see some of the word problems later. All right, so for example, let's say we're talking about some rabbits. Rabbits, they like to have a lot of babies, okay? And babies, when you have rabbits, grow exponentially. So let's say there were initially 8 rabbits. Okay, they are growing at a rate of 50%. Per year. How many rabbits would there be after 8 years? All right, so now I'm going to take this information, I'm going to plug it into my formula. So I'm going to get y equals 8, the original amount, times 1 plus 0.5 to the 8th power. Y equals 8 times 1.5 to the 8th power. I now have a nice simple expression I can plug into my calculator. You can use your calculators for these, obviously, in order to do the exponents. I don't expect you to multiply out 1.5 times itself 8 times. All right, I don't have one on me, but you plug that in to get blah, 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 rabbits. All right, so I did go back and put it into the calculator, just so you know that if you plug this in, you end up with 205.031 rabbits. So as you can see, the power of exponential growth, 8 rabbits becomes that many after just 8 years. All right, so that is our exponential growth model. Initial amount times 1 plus your growth rate to the t power, usually being years, gives you your new amount. All right, so in order to make this a decay model, what do you think is going to change? Yeah, the rate. All right, instead of growing by 20%, maybe it's decaying by 20%. So instead here now, all it changes, this becomes, again, if you do go ahead and plug this in, you get 0.03125 rabbits. Obviously, there are no rabbits left. The power of exponential decay. Unfortunately, it's probably some tiny decimal amount. Poor rabbits. All right, so that is our exponential growth and decay model. You'll be looking at some problems in your homework, looking at calculating things that are growing or decaying. All right. All right, so moving on, we talked about this being our formula for exponential growth or decay. More specifically, y equals a times 1 plus r to the t. This is our exponential growth or decay model, where if it's decay, it would be, of course, minus r. Okay? Many things can grow or decay, not necessarily just money. But one of our most applicable things is indeed money. Looking at money in your bank growing, hopefully growing, exponentially. And it's basically the same formula, except slightly altered. It now looks something like this. Y equals a times 1 plus r divided by n to the nt power. So this whole expression here right now, 1 plus r over n, is being raised to the nt power. So everything from before stays the same, except we have this new n. So again, let's go over what they were. A, this is your initial amount. So if you're putting money into the bank or the CD or the stock market, whatever it may be, how much did you put in? Okay? This 1, we can talk about before, but it just represents this being multiplied by 1 plus the rate. All right? The R, again, is now your interest rate. Common, like, good interest rate would be, like 8% per year. If you're getting that on your investments, that's a pretty good rate. T, again, still time. So N, this is new amount, this new variable, represents the number of times compounded in 1 year. Okay? So oftentimes if you look at different bank accounts or different types of investments, it'll tell you how often your money is being compounded. It can be compounded a few different ways. One way is that it could be compounded yearly, meaning at the end of the year, they apply this formula, spits out your money. Not the best one. Next one, it could be compounded quarterly. How many quarters are there in a year? There's 3 quarters. It could be compounded monthly. How many months are there in a year? 12, right? It could be compounded yearly. Sorry, typo, not yearly. Daily. Yes, just making sure you're paying attention over there. Yeah, you in the back. I see you falling asleep. Okay, daily. How many days in a year? 365. I know there's 0.25 extra, but for the sake of ease, we're going to use 365. Okay, and there's actually one more, which is a completely different formula, but we don't use it for now, but it can be compounded continuously. All right, meaning every moment, every second of the day, it's being compounded. Now, which do you think is the best for your money to be compounded? Calculated once a year, 3 times a year, 12 times a year, 365 times a year, or continuously? Yeah, obviously, the more times it's being spit into this equation, the more interest you're gaining on top of that interest, the more your money will grow. Now, it doesn't make a huge difference, but each time, if you look at the formula and you plug it in, you'll get a little higher amount. So if they tell you it's compounded yearly, n is 1. Quarterly, plug in 3 for n. Monthly, plug in 12 for n. Daily, 365 for n. And lastly, continuously, how do you plug in something to represent all the time? Well, we'll talk about that later. All right, but use a special number called E. All right, so let's take a look at an example. Okay, let's say I've got $1,000 that I just got in my nice shiny hongbao, and they randomly gave me US dollars because my mom's aunt is ABC. All right, so I've got $1,000. I put it into a bank account that I found here in Shanghai. Yes, they accept US dollars, and they're giving me 7% interest. I want to leave it in there for 5 years. I'll go ahead and now plug this all in. So I'm going to get y equals 1,000 times 1 plus 0.07. Don't forget to change this to a decimal. Divided by, oh wait, how often is it compounded? You got to know how often it's compounded. Let's say it's compounded daily. Most banks will compound your money daily. If not, if you're doing it only monthly, you should find another bank. All right, compounded daily. So n is 365 raised to the 365 times t power. T in this case being 5. All right, now you got to be careful. Make sure you multiply those together first before you use it as the exponent. Okay, your calculators, may need to put this in parentheses, all right, so that it knows to put those together. All right, so you go ahead, plug this into your calculators. It'll spit out your final value and tell you exactly how much your money is worth. All right, now what I want you to do, I want you to see how does it change from equation to equation. So I want you to do the same thing. I want you to do it with yearly, where n is 1, quarterly, where n is 3, monthly, where n is 12. We just did daily, and then don't worry again about continuous. All right, how much more money is it making each time? And you'll be able to see how it is better to do it daily. All right. All right, for those of you who are like, why did he talk about continuous interest if he's not going to tell us what it is? Just for your sake, if you don't want to listen to this part, it's fine. Here's the formula for continuous interest. It's y equals p times e to the RT power. Easy way to remember it, PERT. Okay? Or in this case, p is your initial amount. Why do they not use a like we used before? Because PERT sounds better than AYERT. All right? R is still your interest rate. T is your time that you leave it in the account. What is E? E is another special number like pi or phi. Okay? If you look on your calculators, you'll probably see some E and you're always like, what is that E? E is another special number that comes up often in math, and they decided to give it its own special number. E is approximately 2.71 something something something. Okay, if you want to know, plug it in your calculator. All right? But if you were to use this on that same example we just did, you will see that it should be similar to the daily, but it'll be a little bit more money. All right? So daily came out to be $1,419.02, whereas you can see if you plug it into the PERT formula, continuous interest gives you $1,419.07. So only 5 cents more, still a bit more powerful than daily compounded. All right, just to recap things, let's go over our 3 main equations that you need to know in order to do the word problems from these sections. Our growth model, our decay model, and our compound interest formula, all involving some of the same variables. A, in all the cases, is that initial amount that you're putting it in, whether it be money, or whether it be bacteria, or whether it be trees, or the value of a car that's increasing or decreasing exponentially. All right. R is the rate at which it is growing or decaying. 8%, 10%, 12%. Just make sure you put it in as the decimal. T is the time period at which it is growing or decaying. All right. Usually it's years, but it could be in like chunks of months, like I had mentioned earlier. All right. Lastly, N for this one is the number of times compounded per year. So if it tells you it's compounded those specific amounts daily, monthly, yearly, put put in the specific number for n. All right. So again, exponential growth and decay, much different than simple interest, much different than linear growth. These are very powerful formulas, okay? Specifically with money. Remember, Albert Einstein, a very bright guy, said that compound interest is the eighth wonder of the world. Those who understand it, gain it. Those who don't, pay it. Make sure you're one that understands it. All right? Have a good day. We'll see you later. Lastly, I put all of the different compounds into a graph just so you can kind of see what they would look like. First one being yearly, second one quarterly, third one monthly, fourth one daily, and last one continuously. They're all pretty similar, not much of a difference, but each time your money is getting a little bit more, being a little bit stronger, showing that the more you compound it, the better it is. I zoomed in on the 5 different ones just so you can kind of see where they're at. As you can tell, they get a little bit closer each time. The continuous and the daily are so close together that they're almost on top of each other. If I were to zoom in a little bit more, you'd be able to see the purple one just a little bit better than the daily.